Okay, so bringing back these energy systems, we talked about anaerobic energy. Now let's talk about aerobic energy. So you'll see that once we get to this almost entirely aerobic glycolysis, the exercise intensity is a lot lower. And that's because we can't sustain the super high exercise intensity for long periods of time because we don't have enough efficient energy systems to fuel those exercises. So we can generally do aerobic exercise for much longer periods of time because it's at a lower intensity. So that's when oxygen is required. So once we have oxygen fueling our energy, we're able to clear lactic acid and not become as fatigued as quickly. So after about a minute to 2 minutes of exercise, we're using exclusively or almost exclusively aerobic glycolysis. And that's because oxygen is being used by the muscles to generate ATP. Now, this is both fat and carbohydrate or glucose metabolism. So both require oxygen to be converted into ATP to fuel exercise. Fat is a bit slower and used at rest or low intensity, partially used at steady state, whereas glycogen or glucose are a little bit faster and are used more prominently at higher intensity or longer durations of exercise. So let's get into the metabolic cart now, which is primarily what's used to analyze aerobic exercise. So the metabolic cart is the actual physical like cart setup with the computer and has really nothing to do with like the treadmill or that equipment. So the metabolic cart is used to precisely measure oxygen and carbon dioxide that's exhaled. So through the calibration process that you'll learn, the metabolic cart knows what the room air is. And so then whatever is in your expired air, that's the difference between room air and what your body used during the activity that you're doing. So we can use the metabolic cart for a lot of different things. One is like exercise testing, where you have someone on a treadmill or a bike, or any stationary modality that you can collect the gases through this mouthpiece. It can also be used to assess someone's resting metabolic rate, which is just the calories required for your body to do absolutely nothing. So how much your body burns just by resting. Instead of a treadmill and this mouthpiece, that would be attached to this bubble chamber where the individual just lies down in a resting state. And all of their gas in this bubble is taken up by the metabolic cart and analyzed to determine what their resting metabolic rate would be. So both of these use the metabolic cart. We'll only use it for exercise tests during class, but it can be used for other things related to resting state and energy expenditure. So essentially, by collecting all of these gases that are expired by the participant, we gain a lot of information related to their fitness level and their caloric expenditure just by knowing their oxygen uptake and how much CO2 they expire. So the way this works is by analyzing what was uptaken by the body during whatever activity you have them doing with this mouthpiece on. So this mouthpiece has one-way valves, so it only collects expired air. So the only air that's going into the metabolic cart chamber is what you expired. And then you're inhaling room air from the other side of the mask. So when we inhale air, we know it goes into the lungs, and then that oxygen that's in the lungs is diffused into the bloodstream. So that oxygen is carried from red blood cells through the blood and then delivered all over the body to organ systems, to muscles, to the brain, and the oxygen diffuses through the capillaries at all these different sites to be delivered to be used for energy. So after it's diffused wherever it needs to go, it creates carbon dioxide as a byproduct. That's a product of using the oxygen, and that is your body wants to get rid of that. So that takes it back out up to the lungs to be expired. So at the capillary level, we have something known as AVO2 difference. So on this side is where the oxygen is being carried through the arteries to the capillaries. And the capillaries are at the organs, the muscles, the brain, all of that. So the arteries carry oxygenated blood. The oxygen diffuses to the site that it's being delivered to. And then the deoxygenated blood is carried back up to the lungs to get rid of the carbon dioxide through the veins. So the difference in the amount of oxygen between the artery and the vein, or the AVO2 difference, is how much oxygen your body took up and used. And the amount of oxygen your body can use efficiently is a really good indicator of your fitness levels. So the metabolic cart is just capturing what that difference is, because it knows what the room air is made of, how much oxygen and CO2 is in the air that you're inhaling. So whatever you expire, whatever that difference is, that was used by your body. So then we're able to understand how much oxygen your body's using. So we quantify the amount of oxygen your body uses in a couple of different ways. So we have absolute VO2, which is just the liters of oxygen that you consumed per minute, and that's consumed by the body. So whatever was missing from between the room air to the expired air. Relative VO2 is just slightly different in that it's adjusting for body size. So we would expect a larger person to consume more liters of oxygen per minute just because there's more places for the oxygen to go. So then we can use relative VO2 where it's milliliters of oxygen per kilogram of body weight per minute. So this is just relative to the individual. This is just absolute measures. Now, most of the time I hear a lot of students refer to VO2 max only, but we actually are rarely using VO2 max because that requires a full max protocol to get to max, where they reach volitional exhaustion and they reach all these different criteria to make it a true max test. So VO2 max is, yes, a great indicator of someone's fitness, but the numbers you observe on the cart are just absolute or relative VO2 at a sub-max level. So the individual is not performing at max effort, so they are not at their VO2 max. So we have max, which requires a max protocol, submax, which does not require you to reach max and is generally a safer, easier to use, more attainable protocol for most people, where they exercise at a lower intensity. And then based on whatever protocol you use, there's generally prediction equations to predict what their max would be, that use their submax VO2 or their heart rate or any number of variables to estimate what their VO2 max would be. But that is submax, or their VO2 at a level that is not maximal effort. And then you may also hear VO2 peak. This is similar to max, but not quite there. So some exercise protocols, an individual does not reach their VO2 max. So say you're a runner, but you're doing a bike protocol, you're probably more likely to get fatigued before your true max doing that bike protocol. So whatever's the highest VO2 you reach is your VO2 peak. It's kind of a replacement for VO2 max that's just a little bit different. So those are the distinguishing factors between those three different terms. So make sure you're not always saying VO2 max if you don't truly mean VO2 max. So the other variable that you can get from the metabolic cart is RER, or respiratory exchange ratio. So this is the ratio of expired CO2 over consumed oxygen. So how that ratio changes is a good indicator of what fuel source you're using during that time. So RER ranges from about 0.7 to about 1.0, where an RER of 0.7 indicates almost exclusively fat metabolism. So this would be closer to 0.7 if you're at rest or a very low intensity, because as we know, fat metabolism gives us a lot of ATP, but it is slower than carbohydrate metabolism. So when we don't need a lot of energy very rapidly, fat metabolism is a good fuel source. So that's why we'd expect that at rest or low intensities, as opposed to an RER of 1.0, which indicates almost exclusively carbohydrate metabolism. So if you see an RER of 1.0, that would indicate this person is working at a very high intensity or nearing their maximal effort, because as we know, or hopefully know, fat metabolism and carbohydrate metabolism work really well together. So if we're using almost exclusively carbs, that's not a sustainable form of energy and will likely be getting fatigued soon. So 1.0 would indicate near maximal effort or at maximal effort and exclusively carbohydrates. What we expect typically during usual exercise or low intensity activities would be some mix of the two, as they do work together. So, at steady state exercise or something that you think you could sustain for long periods of time, you'd expect something around zero point 0.8. If that's a little bit higher intensity but still sustainable, maybe 0.85, zero point 0.9. But some mix of the two fuel sources is what you would typically observe unless you're doing a maximal test. So, the way that this ratio works, of course, is by expired CO2 over consumed O2. So, with carbohydrate metabolism, you produce a lot more carbon dioxide byproduct. So it's not really this O2 consumed that's driving the changes in this. It's more about the expired CO2. So if you are producing a lot more CO2 byproduct with carbohydrate metabolism, that number is going to get larger and closer to where the consumed O2 is to get an RER of 1, as opposed to fat metabolism, which doesn't produce as much CO2 byproduct. This number would be lower and have you closer to this 0.7 value. So just to summarize, we know that with aerobic metabolism, we need both oxygen and a fuel source, usually carbohydrates or fat. The better our bodies are at using oxygen efficiently, the better we are at aerobic exercise generally. So a higher VO2 max is indicative of higher aerobic fitness, and higher fitness is related to better health and health outcomes and better performance of aerobic activities.